Hello everyone, and welcome to EMNLP 2025, where we are here to present our work, Offloaded Reasoning, Efficient Inference for Large Language Models via Modular Reasoning and Refinement, conducted at Samsung R&D. To begin with, here's some background context for our work. These days, there has been an increase in the popularity of reasoning-capable large language models. These large reasoning models generate a reasoning trace, or chain of thought, before generating the final answer. That is, when a prompt is passed, the model begins by generating tokens belonging to the reasoning trace. These tokens are marked by the special think tags before and after the trace. Finally, once the model finishes generating the reasoning trace, the final response is generated. However, in most cases, these reasoning traces can be quite long. To showcase this, we have a short demonstration. Here, we use OpenAI's GPT-OSS 120 billion and prompt it with a math question. Inspecting the response, on the left-hand side we see the reasoning component, while on the right-hand side we see the final answer. Clearly, the reasoning trace is much longer than the final response, and in fact, in this particular case, the model spends over 76% of its test time compute on the reasoning alone. This brings us to our problem statement. How can we reduce this latency caused by the reasoning process? The method. We propose two training-free approaches which attempt to tackle this problem. Offloaded reasoning, henceforth referred to as OR, and offloaded reasoning with refinement, or ORR. ORR provides appreciable latency improvements while retaining or even superseding the accuracy over the baseline. On the other hand, OR adopts a much more aggressive strategy which provides huge latency speedup gains while taking a minor hit on the accuracy. Before we go into these in detail, let's take a look at some notation. Our methods consist of two large language models of different weight classes, a larger one, which we represent as ML, and a smaller one, represented as MS, both of which are reasoning capable. For clarity, we distinguish between the two generation phases, that is reasoning and the final answer response, using R and A respectively. Using this convention, given an input prompt Q, the standard generation process for such reasoning models looks as follows. The large model ML maps the query to the answer by internally generating a reasoning trace, that is chain of thought RL, where RL equals freason of Q and ML. Moving on to OR, the reasoning component, that is freason, is offloaded to a smaller model MS, which generates an offloaded reasoning trace R hat. This offloaded reasoning trace is then fed back to the large model as a starting point for generating the final answer. This process enables the large model to focus solely on the synthesis of the final answer while delegating the expensive reasoning task to a smaller, less expensive model. This ultimately leads to significant reductions in the inference cost. We can extend the setup established so far by allowing the large model to refine or extend the offloaded reasoning trace generated by the smaller model. That is, instead of immediately initiating the synthesis of the final answer A, the large model is allowed to compute a refined reasoning trace, that is R star, using the offloaded reasoning trace R hat. This refined reasoning trace is then used to synthesize the final answer. Extending the reasoning process in such a manner allows the larger model to retain control over the correctness while still benefiting from the structure bootstrapped by the smaller model. Experimental settings. In order to establish the effectiveness of our techniques in reasoning-heavy setups, we evaluate OR and ORR on two well-established mathematical reasoning benchmarks. GSM-8K, which consists of over 8,000 grade school math problems, and Math 500, which comprises of 500 challenging math problems derived from the math dataset. Regarding the models, in our experiments, the smaller model, that is MS, is a 1.5 billion parameter Quen-based distill of the popular DeepSeek R1 model. For the choice of the larger model, that is ML, we experimented with the following models, ranging from 7 billion to 32 billion parameters. Evaluation consists of computing accuracy and latency metrics for each model dataset combination. For measuring accuracy, we borrow the methodology from the popular framework LightEval and compute exact match in case of GSM-8K and pass at 1 for Math 500. Latency is computed in terms of average inference time, that is, seconds spent per query, averaged over all the examples in the dataset. Results. Offloaded reasoning enables efficient reasoning and provides drastic speedups over the baseline. For example, in case of the 7 billion model with OR, we observe over 7 times reduction in latency compared to the full 7 billion reasoning. At the same time, it improves accuracy over the standalone 1.5 billion model. Similar trends are observed across weight classes. This establishes that offloaded reasoning offers a superior quality efficiency trade-off compared to both small and large standalone reasoning models. Refinement boosts quality. For instance, on GSM 8K, ORR achieves an exact match score of 88.70, outperforming both 7 billion full reasoning and 7 billion offloaded reasoning. As we can see, once again, trends generalize across the model sizes. This indicates that large models can effectively refine and enhance imperfect reasoning traces generated by the smaller models. To test the modularity and transferability of our methods, we applied the 1.5 billion model's reasoning traces to a different response model family. In this case, a llama-based 8 billion parameter distill of the DeepSeek R1. Once again, OR and ORR both outperform the same 8 billion model's full reasoning in terms of both accuracy as well as latency. This highlights the plug-and-play nature of a method for production use cases. To summarize, offloaded reasoning with refinement uniquely combines modular reasoning, efficiency, and robustness in a unified framework. Our methods provide a way of orchestrating small and large models for reasoning and refinement, resulting in significant inference gains without compromising accuracy. This modularity also enables dynamic scaling, making it highly suitable for real-world deployments with variable compute budgets. With this, I conclude my presentation. In case you have any queries or would like to discuss further, please feel free to reach out to us at our emails listed here. Thank you so much for your time.